And finishing up with 9E. So for 9E, continuum limit of a chain of coupled masses and springs. So consider identical masses M separated by equilibrium spacing A and connected by identical springs. Let Q sub j of t be the transverse displacement of the jth mass, and for small transverse oscillations, the discrete Lagrangian may be written as L sub discrete equals the sum over j for 1/2 m q sub j dot squared minus 1/2 kappa times the quantity q sub j plus 1 minus q sub j squared, close bracket, where kappa is the effective nearest neighbor coupling constant, and the equation of motion is mq double dot sub m q sub j double dot equals k times the quantity q sub j plus 1 minus 2q sub j plus q sub j minus 1, close parenthesis, and define a continuous coordinate here, x sub j equals ja, and assume the displacement varies slowly over one lattice spacing. Q sub j of t goes to u of x sub j comma t, and the Taylor expand here from here. Taylor expand the neighboring displacements from here. U of x plus a t equals u of x comma t plus a u sub x plus a squared over 2 u sub xx plus a cubed over 6 u sub xxx plus on and on and on with that pattern. And u of x minus a comma t equals u of x comma t minus a u sub x plus a squared over 2 u sub xx minus a cubed over 6 u sub xxx plus and on and on and on. So therefore, u of x plus a comma t minus 2u x comma of x comma t plus u of x minus a comma t equals a squared u sub xx plus big O of that a to the fourth. So the discrete equation becomes m u sub tt equals kappa a squared u sub xx plus big O of a to the fourth. Neglecting higher order terms, u sub tt equals kappa a squared over m u sub xx. So the discrete system approaches the wave equation with c squared equals kappa a squared over m. So identification of the continuum parameters are mass per unit length is rho equals m over a. And to identify the continuum elastic coefficient, we note that q sub j plus 1 minus q sub j is asymptotically equivalent to a u sub x. And the spring energies, that becomes 1/2 kappa times the quantity q sub j plus 1 minus q sub j, that quantity squared, is asymptotically equivalent to 1/2 kappa a squared u sub x squared. And also here the sum over j, that goes to 1 over a times the integral there of 1 dx. So building on that, so sorry about this, we're just gonna continue here. Get this ready. So building on this, so therefore the total kinetic energy, total elastic energy becomes sum over j 1/2 kappa times the quantity q sub j plus 1 minus q sub j squared goes to 1/2 kappa a u sub x squared dx. Comparing with the continuum string energy, v equals 1/2 t u sub x squared dx. Identify t equals kappa a, and then t over rho equals ka over m over a equals ka squared over m, which agrees with the discrete derivation c squared equals t over rho. So the discrete dispersion relation, a discrete normal mode has the form q sub j of t equals a e to the I times the quantity kja minus omega t. And substitution into m, q sub j double dot, that equals k, times the quantity q sub j plus 1 minus 2 q sub j plus, plus q sub j minus 1, close parenthesis. And that gives negative m omega squared equals kappa times the quantity e to the I kappa a minus 2 plus e to the negative I kappa a. So here we wind up with the following. Since we have this sum equals this 2 cosine Ka, and m omega squared equals the following here. For this sum, sorry, using here 1 minus cosine Ka equals 2 sine squared of Ka. The discrete dispersion relation is omega squared equals 4 kappa over m sine squared of Ka. So omega equals 2 times the square root of K over m. Absolute value sine of Ka over 2. And in the long wavelength limit, Ka is much less than 1. And so sine of Ka is sine of K over 2 is asymptotically equivalent to Ka over 2. Omega is asymptotically equivalent to 2 times the square root of K over m. Absolute value Ka over 2 equals A times the square root of K over m, absolute value of K. So W is asymptotically equivalent to C, absolute value K. C equals A times the square root of kappa over m. And this is precisely the non-dispersive dispersion relation of the continuum wave equation, and the continuum approximation is therefore valid when the wavelength is much larger than the lattice spacing, where we have lambda is much greater than A, where Ka is much less than 1. Okay, so that's all for 9E. Thank you very much and have a great day.